So we're going to kind of go back, dare I say, in matrix stuff. We're still working with matrices, but what we're going to do is a lot easier than row reducing matrices. So I feel like it's almost going back to like the beginning of here's a matrix, here's some other things we can do with matrices besides solve systems. And hopefully this will be a little bit of a break from the long problems of solving systems. Matrices can be added and subtracted. In order to add and subtract, you must have exactly the same dimensions. And remember, dimensions means the rows and the columns have to be identical. So if your first one is 2 rows and 2 columns, your second one is also 2 rows and 2 columns. Once we verify that they have the same dimensions, what we are going to do is we are going to add the pieces in the same position. So add, I guess, or subtract the terms in the same positions. Okay, so our first example, we have the matrix 2, 4, 1, 7. And then the next matrix is -1, 3, 0, 4. And our goal is to add those two matrices together. All right, so the way that we do that then is you're just going to work place by place. So we know we have 2 by 2, 2 rows, 2 columns. So I know my answer is also going to be a 2 by 2, 2 row, 2 column. And then I'm going to work upper left first. So 2 plus -1 is 1. And then if I go to the upper right, that's 2 plus 3 is 7. And then I work the second row. So lower left, 1 plus 0 is 1. And then the bottom right, 7 plus 4 is 11. So you literally just add piecewise locations to get your final solution. So we can look at our next example here. We have a 3-row by 2-column matrix. So 3, 2, -1, -1, 0, 3 is that first matrix, plus -2, 3, 1, -1, 2, -2. Long as our dimensions match up, we know they do. They're both 2 by 3s here. Sorry, 3 by 2s, 3 rows, 2 columns. We're just going to add piece by piece. So 3 plus -2 is 1. 2 plus 3 is 5. First row done. And I go second row, -1 plus 1 is 0. -1 plus -1 is -2. 0 plus 2 is 2. And 3 plus -2 is 1. Make sense? Pretty straightforward. Easier than all the row options, reductions, and everything we've been doing. So hopefully this is a nice little break. I want you to look at this one. First one is 1143, and it wants us to add it to 1026 negative 15. And the look on Emily's face right now, she's like, Steven's over here shaking his head. No. Why can't I do this? They're not the same dimensions. They don't even look the same, okay? So they have to look the same. You have to have the same numbers across and down. So this, we would say, you can call it like a dimension mismatch. So the dimensions, meaning the rows and the columns, is the dimension mismatch. The answer then is undefined because I cannot actually perform this operation. But it's pretty easy to see that I can't perform it. Like they're clearly not the same size. All right. So what I suggest when you come across a subtraction problem is probably very similar to what you would do in algebra when you were adding and subtracting polynomials. So I kind of treat it that same way. And I will change A minus B. So matrix A is the first one, minus B, B is being the second matrix, into A plus negative B. So what I'm doing is I'm distributing that negative into everything in that second matrix, and then setting it up as an addition problem and adding piecewise position across the matrix. So this matrix is 2, negative 3, 5, and we want to subtract the matrix 3, negative 2, 1. So what I usually do first is I take the negative and I'm going to distribute it into everything here. So I'm going to keep the first one, 2, negative 3, 5. When I distribute this in, I'm then going to put a plus, and I'm just changing the signs on all of these. So negative 3, positive 2, and negative 1. Now, in the end, do you have to do this? No, it just eliminates some of the mistakes that can happen by common error. So I'll show you after we do this how I would have done it if I didn't want to write this intermediate step. So piece by piece, 2 plus negative 3 is negative 1. Negative 3 plus 2 is negative 1. And 5 plus negative 1 is 4. So other option is just making sure that instead of adding each pair of terms, you're subtracting. So 2 minus 3, you're thinking 2 minus 3 is negative 1. You're thinking negative 3 minus negative 2, that turns into negative 3 plus 2 is negative 1. And then 5 minus 1, which is that same 4. The trick that the error that happens is sometimes when there's that subtraction, I've seen it all the time in algebra, is you subtract the first one and maybe the second one, and then, oh, by the end, it's like, oh, 5 plus 1 is 6, and you go back to adding because you forget that that's a subtraction in between there. Our brains default to that addition a little bit faster than the subtraction. So do I care which method you use? No, this just has a chance to eliminate errors that I've seen happen. So we want to find A, B, C, and D in the first matrix that would make this final statement true. So my first matrix is A, B, C, D. I want to subtract the matrix -4, 2, 1, -3. And I want to get the result -2, 5, 8, and 2. All right, so if I work piece by piece, this is saying A minus -4, so just working upper left here, is going to equal -2. So that means what? A plus 4 equals -2. We can solve this, right? Subtract 4. A is -6. Done. And then we just keep working. So now if I work upper right, that's B minus 2 equals 5. What minus 2 gives me 5? Yep. Next one down here would be C. So C minus 1 equals 8. What number, if I subtract 1, gives me 8? 9. Beautiful. And then we have D. So D minus -3 equals 2. That means D plus 3 equals 2. Subtract 3, -1. So you can easily find a missing value in a matrix by just breaking it out into the pieces you're working with. Any questions on that? All right, so then the next thing we're going to do is what is called multiplying by a constant. So multiplying by a constant literally means you're going to distribute it through to every single piece inside. It's just like if it was parentheses. The number that's out front goes to everything on the inside. All right, so distribute to all, capitalized, underlined, and bold, however you want to write it, terms inside the matrix. Now, did we do a little bit of multiplying with our matrices when we solved them? Yes, but we only multiplied a single row by a value. Now we're going to multiply everything through by that number. So this wants us to take 4, multiply to the entire matrix, 1, -3 half, 6, 2, -3, 1, 1/4, and 10. So literally all I'm going to do is multiply everything by 4. 1 times 4 is 4. 4 times -3 is -12. 4 times a half, 2. 4 times 6, 24. 4 times 2 is 8. 4 times -3 is -12. 4 times 1 is 4. 4 times a fourth is 1. And 4 times 10, 40. The next one combines both things, multiplying by a constant and then adding / subtracting. So we have 3 times the 2 by 2 matrix, 1, -1, 4, 2, minus 2 times the 2 by 2 matrix, 0, 6, -2, 8. So the first thing I'm going to do is distribute in the 3 and then distribute in that -2. So let's see, that first matrix is going to be 3, -3, 12, and 6. I'm going to distribute in the -2 to turn this into an addition problem. So -2 times 0 is 0. -2 times 6 is -12. -2 times -2 is 4. And -2 times 8 is -16. And then from there, we are good to just add position to position. So let's see, 3 and 0 make 3. -3 and -12 is -15. 12 and 4 is 16. 6 minus 16, -10. Okay, any questions that we have for multiplying by a constant? Okay, this is the, dare I say, hardest thing we're going to do today. It is called matrix multiplication. So now we want to multiply matrix A by matrix B. So the definition here says, let A be an M by P matrix and B be a P by N matrix. Then the product of A and B has dimensions M by N. To get any term in the Aij position, so any term in a corresponding row and column position, it's found by the product of the row in A and the column in B. It's a lot of words. We will practice a few of these so you can understand what we're doing. And then for our first example, our first matrix is -1, 0, 3, and 2 all in a row. We're going to multiply by the column matrix 2, 3, 4, -1. Anytime you are multiplying matrices, write the dimensions underneath them. So this is 1 row by 4 columns. This one is 4 columns by 1 row. Okay, I can do 1 by 4 times a 4 by 1. Your middle pieces here must be the same in order to perform the matrix multiplication. Okay, if these are not the same, you cannot do the multiplication. There's no answer, not defined. We have a dimension mismatch. Then the values on the outside are your solution. So a 1 by 1 is what our final answer is going to be. It's literally going to be one term. So I have 4 terms here, 4 terms here, and I'm going to multiply, and I'm only going to end up with one value when I'm done. So the way we do this multiplication is position to position, row paired with column. So in order to get this term, A11, you are going to multiply the terms in row 1 by the terms in column 1 of this other guy here. Okay, so row 1 times column 1 values. Now there's 4 values there, so we are going to work piece by piece and create a string. So that's -1 times 2 is the first, plus 0 times 3, there's the second, plus 3 times 4 plus 2 times -1. So you're going to multiply the terms in their corresponding positions and then add all of the results together. So let's see, that's what, -2 plus 0 plus 12 plus -2. So 12 minus 2 is 10, minus another 2 is 8. So 8 is the final result. Let's look at a 2 by 2 times a 2 by 2. So first matrix, 2, -3, 1, 2 is being multiplied by 1, -1, 0, 2. I have a 2 by 2 that I'm multiplying by a 2 by 2. The middles are the same, so we can do this, and the final result will be a 2 by 2. Now, in order to get the upper left spot here, we take the first row. We want row 1, column 1. That's where this location is, right? Row 1, column 1. So we're going to take row 1 times column 1. All right, so if I do the math, oops, 2 times 1 plus -3 times 0. That's going to be that first spot there. Okay, the next spot over here is row 1, column 2. So I'm going to take row 1 times column 2. And do that math. So 2 times -1 plus -3 times 2. I clearly made a massive matrix here. All right. Next spot is row 2, column 1. So I'm going to take row 2 times column 1. My goodness. So 1 times 1 plus 2 times 0. Need a lighter color. Oh, try. All right, this spot down here is row 2, column 2. So I'm going to take row 2 times column 2. So 1 times -1 plus 2 times 2. So when you're doing the matrix multiplication, you're always using the rows of the first matrix and always using the columns of the second matrix. All right, so final answer here. This is 2 plus nothing, 2. -2 plus -6 is -8. 1 plus nothing is 1. -1 plus 4 is 3.
And the second step was row 1 times column 2.
Yes. So this is row 1 times column 1. I always miss the N there. Row 1 by column 2, row 2 by column 1, row 2 by column 2. Because that's the actual location that this value is. So that's how you go back to the initials. Good question. All right. You take a look at this one. -1, 0, 3, -2, 1, 2, 2, 0. So this is a 2 row by 4 column times -1, 1, 2, 3, 1, 0. So initially, I can already see there's 8 numbers in this first one and 6 numbers in the second one. So it's not going to work because there's no way to pair up 8 numbers with 6 numbers. Okay. So if I wrote this down, it's 3 by 2. This does not match. So again, that is called a dimension mismatch, meaning it is undefined. It cannot find an answer for this because the numbers do not match up. Okay, I'm going to skip this one just because I have one more example that's another 2 by 2. And if we need a third example of it, I'll come back and do this one. But I'm going to look at this one first. And then you guys can tell me if you want me to go back and do another example. All right, if B is the matrix -2, 5, -1, 3, find B squared. So the first thing we need to remember, what does it mean to square something? Multiply by itself. So I'm taking this matrix and timesing it by itself. Okay, so we are going to do this multiplication again of another 2 by 2 multiplication. All right. So, row 1, column 1. Row 2, nope, row 1, column 2 is over here. Row 2, column 1 is down there. And row 2, column 2 is over here. All right, so I need row 1 with column 1. Row 1 with column 1. -2 times -2 plus 5 times -1. So what does that give me? 4 minus 5 is -1. Okay, next one is row 1, column 2. So row 1 pair with column 2. So -2 times 5 plus 5 times 3. So that's -10 and 15. Add those two together. Gives me 5. All right, row 2 with column 1. So -1 times -2 and 3 times -1. 2 plus -3 is -1. And then my last one here, row 2 times column 2. -1 is going to multiply by 5. 3 is going to multiply by 3. -5 plus 9 leaves me with 4. Do you need me to do another example, or are we okay? Good. Okay. I only have one more example and then we are done for today. All right, we have a cost analysis example here. There's a company with two different plants, manufactures guitars and banjos. Its production costs for each instrument are given in the following matrices. So we have two separate locations that are both making guitars and banjos, and we are keeping track of the materials and labor costs. So plant X is the matrix 47, 39, 90, 125. So that's material costs and labor costs. And then plant Y, our guitar, some materials, $56, $42 for banjo. Labor is $84 and $115 for guitar and banjo, respectively. So this one says find 1/2 A plus B, the average cost of the production for the two plants. All right, so let's see. 1/2 times matrix A 47, 39, 90, 125 plus 56, 42, 84, 115. Okay, order of operations. Am I going to do the distribution first, or am I going to do what's inside the parentheses first? Parentheses first. So I'm going to add these two matrices together first, and then I'm going to have all of them. All right, so if we take 47 plus 56, that's $103. 39 plus 42, 81. 90 and 84 makes 174. 125 plus 115 is 240. So what this is doing is this is now the combined cost for making a guitar at both locations, making a banjo at both locations. So materials and labor. Now I'm going to have every one of those. And we would get $51.50, $40.50, $87, and $120. Okay, so this is still guitar, banjo, materials, and labor. But now this is giving me, because I have two plants, this is now the average cost. So average cost in materials to make a guitar is $51.50. Average cost to make a banjo with materials is $40.50. Average cost for the labor of that guitar is $87. Average cost for the banjo labor is $120. So you can just see how I'm still talking about guitar materials, guitar labor. It's just that instead of it being at plant X, plant Y, these are now all the average costs across my facilities. I lied. There is one more after this. I apologize. It got blended into my other notes here. I thought this was the last one. Makes sense? Average, you add two things together and then you divide by 2. Anytime you find an average, if I had 5 plants, I would add all 5 plants and then divide by 5. All right, last one here. In a local California election, a public relations firm promoted its candidates in 3 ways: telephone calls, house calls, and letters. The cost per contact is given in matrix M. So you can see here, M is the cost per contact. It costs this company $1.20 for every phone call, $3 for every house call, and $1.45 for every letter. The number of contacts of each type made in 2 adjacent cities is in the second matrix. So we made 1,000 telephone calls, 500 house calls, and 5,000 letters in the town of Berkeley. And in the town of Oakland, 2,000 telephone calls, 800 house calls, 8,000 letters. All right, so find the total amount spent in Berkeley. So knowing that this is Berkeley, so I'm only working with Berkeley. There were 1,000 telephone calls, 500 house calls, 5,000 letters, and I know the corresponding costs for each of them. Right? $1.20 for a telephone call, $3 for a house call, $1.45 for a letter. What am I going to do with those numbers to find my answer? Multiply. So 1,000 times $1.20 plus 500 times $3 plus 5,000 times $1.45. So I'm literally just matching up how many multiplied by how much it costs. If I do that, I'm going to get 9,950. Now they want us to do the exact same thing, but with the other town of Oakland. So we have 2,000 phone calls times $1.20, 800 house calls times $3, plus 8,000 letters times $1.45. And this one, all you got to do is type it in a calculator. You're going to get $16,400. Oops, wrong button. Last question. If either MN product of MN or NM has a meaningful interpretation, find the product, label its rows and columns. What do the entries represent? So let's look here. M by N or N by M. Well, M is 3 rows by 1 column. N, 2 rows by 3 columns. Okay, am I going to be able to do that multiplication? No. All right, if I write N first, 2 rows by 3 columns, N is 3 by 1. Am I going to be able to do that one? Yes. Okay, I am taking the rows of N and multiplying by the column of M. Is that not what we just did up here? Did I not just take the row and multiply by the column? And then the row, and again, multiply by the column to get these answers here? Okay, so when I actually do this operation and take this row by this column, I get that value, 99.50. When I take the second row times the column, I get 16,400. So what is this result? What is this matrix giving me? What are my rows and my columns telling me? Total amount per city. So exactly. So total cost per city. So the column is still the cost, and your rows are Berkeley and Oakland, the cities. There you go. A nice break from solving systems. All right, well, that is all I have. And I want to say this is the end of chapter 4. I believe we go into chapter 5. Oh, no, we have one more section. Okay, so we're going to talk about inverse matrices and applications with those, and then we'll be done with matrices. So one more extra thing, one or maybe two things we'll talk about with matrices next week, and then we'll move into chapter 5, which moves into the concept of like graphing linear inequalities. So it's like graphing lines, but shading, and then finding where your potential solutions are, and a process of linear programming. All right, so that means homework for 4.3 and 4.4. Work on that over the weekend. That is due on Tuesday. No quick check today, just because I felt like this was a little more straightforward. I trust that this is a little easier and that we don't need to walk around and double check how we are doing. But if you feel otherwise, like I have another class here, not for like 45 minutes, but I will hang around if you need me. All righty.